Hello, in this video, we will be presenting the Salience-guided ground vector for robust localization of delivery robot in complex urban environment. Most autonomous delivery robots navigate complex urban environments. However, due to the nature of the urban environment, there are many GPS-denied areas which makes localization difficult. To address this, we utilize ground information for localization that is robust to a variety of adverse conditions. To utilize the ground information, the front image can be projected as a broader view by applying inverse perspective mapping. However, traditional IPM methods suffer from distortion in the broader view image when motion changes occur. In addition, traditional methods of using ground information rely on standard, predefined, or classifiable markings for localization. However, in the city we live in, there are a lot of ambiguous markings in addition to the standard ones, and we need to respond to these custom markings. We proposed the novel localization method based on molecular camera that solves the distortion problem of IPM and can respond to the custom markings. The proposed method consists of 4 parts, and we define the custom marking covered by the system as a salient ground feature. IPM distortion compensation is complete by improving the formula of existing adaptive IPM that can compensate for the robust pitch motion. Prior to 2D to 3D projection, the compensation for low motion on the image plane can be solved with 2D rotation. Subsequently, geometric constellations of IPM model allow for complete 2D to 3D projection with added lower compensation. The extended IPM formula is shown above, and the detailed derivation process can be found in the adaptive IPM paper. And in the qualitative result on the right, you can see that the affine distortion caused by the low motion is well compensated. Based on monocular camera, it is difficult to estimate the front ground, which prevents immediate motion compensation. Therefore, we accumulate IMU post to calculate the relative difference and use this for compensation. Here is the demo video of Motion Compensate IPM. The video shows the result for uphill and downhills as well as areas of temporarily uneven ground such as speed bump. Salient Object Detection model detect which part of the image scene are considered to be the most important. Using this feature, we aim to extract important features of the ground that are difficult to classify. Salient Object Detection model showed relatively low quality result on the broader image because it takes to shoot for normal scene. So we reformulate the SERM dataset containing several ground markings and the existing training dataset to give the model a tendency toward broad view. To make good use of them, it is important to select the best features that are intact in between their appearance and disappearance. To this end, we define an optimal SGF detector in 4 steps using the moment that capture the nature of the binary image well. First, determine the varied feature range from when the feature appears to when it disappears. Next, calculate the hue moment for all binary images in the varied feature range. After that, calculate the hue moment distance between the previous image and the current image. Finally, select the optimal salient ground feature of the intent shape within the group whose moment distance is less than threshold. When the optimal feature is obtained, the SGF part is extracted in the form of a point cloud using the corresponding Abadabi image. The SGF cloud is downsampled and RGB values are not used in the description to avoid the ambiguity of the illumination. Considering the reverse loop, we describe the SGF cloud to be rotation robust. For this purpose, we adopt the polar description proposed in the scan context and generate a descriptor vector by creating a pointing histogram for each bin. Descriptor can be generated for various SGFs, and online clustering is performed to build an SGF database. If a robot revisits a location with the same SGF as before, it can make an ICP match from the SGF database. If the current location matches the past location, add the relative pose as a constraint to perform the pose graph optimization. As a first experiment, we compare our retrained model with other salient object detection models. We demonstrate the superiority of our performance on the 4 quantitative metrics typical of the task. The following are some sequences with different SGFs for measuring absolute trajectory error. Sequence reverse and slope was considered to evaluate the SGEP matching in reverse loop and motion compensate IPM compensation. This is a postgraph optimization demo video for sequence large loop. If the robot reveals the same SGEP location, post optimization achieves zero SGEP matching. With lobe-mounted light and contrast-limited adaptive histogram equalization, SGEP detection can perform similarly to daytime. Since ground markings only occupy a specific area of the front view, matching is not difficult at night. The trajectory illustration above shows a qualitative result of the optimization using SGEP. Compared to the ORB-3, our method performed more completely. We can also see the SGEP matching is well achieved even in reverse loop, and it achieved robust performance at night. Finally, we compared the optimization result for the proposed motion compensate IPM with the existing IPM. In particular, you can confirm that the function of motion compensate IPM worked effectively in slope sequence. For more information about our work, please visit the project page using the URL shown here. Thank you.